In this video, you will learn how to represent systems of equations using matrices and vectors and how to solve those systems using linear algebra operations and how to represent them graphically in Matlab. So as you all know, a linear equation has only two types of terms, constants and variables multiplied by a constant. For example, say 4x minus 2 is equal to 14 or something. So a linear equation is an algebraic equation, and algebraic equations have an associated picture. And the number of variables or unknowns in the equation determines the number dimensions in the corresponding graph. For example, in this equation, we have just one variable, so this the solution to this equation, which is x is equal to 4, can be visualized as a point on the number line. And we can draw a number line and plot this in Matlab. Now, suppose we have two equations. For example, 2x plus 3y is equal to 16 and 5x minus 4y is equal to minus 6. Now, let's try to solve these equations graphically first. So let's first use the column operator to create a vector of x values over which to plot lines. So x is equal to minus 5 colon 0.5 colon 5. So we have our x inputs. Now let's solve for y from both equations. For the first equation, y is equal to 16 minus 2x my 2x by the whole divided by 3. And for the second equation, the value of y will be equal to minus 6 minus minus 6 minus 5 times x, the whole divided by minus 4. So now let's plot. Let's run this. And now let's plot the lines which correspond to these equations. So for the first line, the command is plot x comma y1. For the second line, the command is plot x comma y2. There should be a hold on command in between. Now let's add a legend to identify the lines. So equation 1, comma, equation 2, and let's write all of and run this here. So when I run this, I get my figure. Now, now the solution of a linear equation, a system of linear equations, refer to the xy pair that makes both equations equal. In other words, the xy pair corresponds to the intersection of the two lines. So this point here, this is the solution to the equations, to the system of equations here. So if I visually inspect the plot, I find that the point is 2, 4. Now we can verify that whether 2, 4 is the correct solution by substituting these values to x and y in the original equations. So we had a 2D graph for equations with two variables. Now it's not always very easy to solve equations graphically for a system of three variables. Let's see. The figure would be three-dimensional. So let's take an example with three variables. So 7x plus y plus 5z is equal to 27. Then 4x plus 3y plus 5z is equal to 21. Then 6x plus y plus 2z is equal to 9. Now, each of these equations have an associated plane. Let's plot them. So we had already seen how we can plot planes in MATLAB in the last video. So let me first create the input vectors x, y using the colon operator and the mesh grid function. So minus 5 colon 0.25 colon 5. Then let me solve for z in these equations. So for the first equation, z will be equal to 27 minus 7 times x minus y, the whole divided by 5. Similarly, z2 will be equal to 21 minus 4 times x minus 3y divided by 5, and z3 29 minus six minus y by 2. And let's plot this using the mesh function. So mesh x comma y comma z1 colon mesh z1 y comma z2, then x comma y comma z3. And let's run this and see what we get. So this is how a system would look like graphically, and there's one point at which all these three planes intersect. The point at which these points intersect is this point over here, which is close, which is 0 minus 3 6. So yeah, this point over here. So it's very hard to see the point at which these planes meet in such a visualization. So, so this is the point at which all three planes meet. If you look closely. Now, this will get even worse when the number of variables increases. So how can we solve these equations? One way is to turn these equations into matrices and vectors. All these equations can be represented in the form Ax is equal to B, where A is called The coefficient matrix, as the name suggests, the matrix A contains the coefficients of the variables of the equation, X contains the variables, and B contains the constant terms of the equation when they are in RHS. So, and the backslash operator solves the matrix equation Ax is equal to B for the vector of unknown variables X. So let's see that. Let me first define the coefficient matrix A, which is 7 on 7, 1, 5, semicolon 4, 3, 5, semicolon 6, 1, 2. Then B, which is equal to B is our is the constant vector. So B is 27, semicolon 21, semicolon 9. And let's solve Ax is equal to B for X. So X is equal to A backslash B. And when I run this, I get my solution 0 minus 6, which was the point where all the three planes met in this graph. Now, both the systems of equations, this system of three variables and this system of two variables, they had the same number of equations as unknowns. So here we had two equations and two unknowns, and here we had three equations and three unknowns. Now, this means that the coefficient matrix A is square. Also, solving them in Matlab gives a unique solution. Now, these systems are called determined systems. Now, there are overdetermined and underdetermined systems. An underdetermined system has fewer equations than unknowns. So, if I copy this matrix here, paste this, and delete the last row from the vector and the coefficient matrix, then I'll get an underdetermined system. So an underdetermined system has equations than unknowns. The coefficient matrix A has smaller number of rows than columns. Now, underdetermined equations generally have an infinite number of solutions. So if I visualize um, this system, so let me plot these graphs. So x comma y comma z1, then x comma y comma z2, all of so, so when you look at this graph here, you can see that there are many valid solutions possible to the system of equations. So all the points in the line formed by the joining of these two planes are solutions to the system. Now, the backslash operator can only return one of them, so it returns a solution with the maximum number of zero elements possible. So, if I write x is equal to, so let the x is equal to a backslash b and run this, a2 backslash b. If I run this, see here, it returns the solution which has at least one zero element if possible. So then we have the overdetermined system. An overdetermined system has more equations than unknowns, and the matrix A has more rows than columns. Overdetermined systems generally have no solution. In this case, the backslash operator finds the best vector using least squares, which minimizes the squares of error in all equations. So, if I have a system like x minus y is equal to minus 2, then x plus y is equal to 0, then x plus 2y is equal to 3. And let's plot these equations on graph. So let me first define my x and x values and find solutions for y in these equations. So for the first equation, y is equal to minus 2 minus x divided by 1 minus 1. For the second equation, it's 0 for the second equation, it's minus x minus x. And for the third equation, it's y is equal to 3 minus 2 times y by 1. And let's plot this. So plot x comma y1, plot x comma y2, plot x comma y3. Let me also add the whole on and all of commands and also a legend to mark the lines, to label the lines. So let me run this. Something went wrong here. So for the third equation, it was 3 minus x by 2. Okay. So let me run this again and see. Yeah. So this is my system. And here it's very difficult to find a solution which satisfies all the three equations. So let's try the backslash operator here. So let me check which point the backslash operator returns. So if I do x is equal to, let me first define the coefficient matrix, which is 1 minus 1 semicolon 1 minus 1 semicolon 1 1 semicolon 1 2 and p, which is minus 2 semicolon 0 semicolon 3. And let's find x, which is a backslash b. So let's see. So this is the point returned by the backslash operator, and let's plot this point in this figure. So let me use the scatter function to prove this. So minus 0.7143 and 1.5714. And let me run this again and see. So it is this point over here which minimizes the squares of error in all the three equations. So now suppose we have singular matrices. It is possible for A to have A to be square, but the system to have no solution or an infinite number of solutions. This happens when the determinant of A is zero. In this case, the matrix A is said to be singular. So for example, if I have the system say A is equal to 1 1 semicolon 1 1 and B equal to minus 2 semicolon 2 and let's plot this. So the equations, the original equations were x plus y is equal to minus 2 and x plus y is equal to 2. So let's see. So first let me define the x vector. Now let me find the corresponding values for y. So y1 is equal to mm, minus 2 minus x and y2 will be equal to 2 minus x and let's plot them in a figure. So x, y1, then all down x, y2 or x, y2. So as you can see here, both lines are parallel. When we plot this, the system of equations is represented by two parallel lines. Yeah. Therefore, there is no point of intersection of or solution to the system or to the system of equations. And when I use the backslash operator here, say x is equal to a backslash b, the backslash operator will warn you if a is singular or nearly singular. So this is all about solving linear equations in Matlab. Thanks for watching. See you guys in another video.